Okay, thank you very much. Thank you for organizing this wonderful workshop and for inviting me to speak. My name is Noa Zilberman. I'm a PhD student of Professor Amos Ori at the Technion in Israel. And today I will talk about semiclassical energy fluxes at the inner horizon of a rotating black hole. So I will start with a short story with an open end. The analytically extended Rising-Nordstrom and Kerr metric, describing respectively rotating and spherical charged black holes, reveal a traversable passage through an inner horizon to another external universe. And this remains the case in the more physically realistic scenario of gravitational collapse, in which only the ingoing section of the inner horizon maintains the role of the Cauchy horizon, which is the boundary of the domain of predictability for initial value problems formulated outside the black hole. Now consider a traveler intending to access this other external universe. In order to do so, she must pass through the black hole interior, and in particular through the Cauchy horizon. What will she encounter along her way? Does this other external universe actually exist? And is her mission doomed to fail? So in order to answer these questions, one would need to understand the manner in which quantum effects modify the black hole interior. And in particular, that would require the computation of the stress energy tensor on black hole backgrounds, especially near the inner horizon. So in this talk, we'll start with some motivation and basic framework. We'll continue with the Unru quantum state, which is the state we are going to consider. Then we will see what is the individual mode contribution to the fluxes. Then we will renormalize using a special state that we are going to subtract. Then I will show you our novel numerical results. And finally, we'll have a very short and preliminary discussion of back reaction. So let's start. Okay, so let's start with the motivation. So it is not a new thing that quantum effects may modify the classical space-time geometry, but already classically, it was shown that classical perturbations may change the otherwise regular black hole interiors. One of these most interesting modifications is the null weak singularity that forms along the otherwise regular Cauchy horizon in both the spinning and charged cases. So it is therefore reasonable to expect that quantum perturbations will also have an effect on the Cauchy horizon. And a general indication that emerges from a collection of analytical studies on the effect of quantum perturbations inside black holes has been that semiclassical energy fluxes are likely to diverge at the Cauchy horizon. So it has been our goal to address this issue via concrete numerical calculation of the actual strength and form of these quantum effects. And we started with the spherical charged case, where our results for the asymptotically flat case and Holland's group results for the de Sitter case confirm the analytic expectation of the divergence of these semiclassical effects at the Cauchy horizon. And so it is the goal of the current work to tackle the more challenging, yet much more physically relevant case of the rotating black hole. So since we are dealing with quantum matter fields propagating on a classical curved space-time, we are going to use the semiclassical formulation of general relativity. So I guess you all know the semiclassical Einstein equation. So the curvature of space-time induces non-trivial stress energy, even in vacuum states. And these in turn deform the metric in an effect known as back reaction. But already on the very initial step that one should take to analyze this equation, it is very challenging, and it has been a great challenge for many decades to compute the renormalized stress energy tensor, the right-hand side here, on classical black hole backgrounds. So this is what we would like to do. So I have to tell you first what is the black hole background that we are going to consider and what is the field under consideration. So our metric is going to be the Kerr metric. It describes a rotating black hole. And this is the maximally extended Penrose diagram. It has an event horizon, an inner horizon, A over M varies from 0 to 1, where 1 is the extremal Kerr. And we are going to mostly consider this red frame over here, where P and I, F and I are the past and future null infinities. HR is the event horizon, or EH sometimes, and IH would be the inner horizon. And the ingoing section of the IH is what we would call the Cauchy horizon. Now for the field. So for our field, we take a minimally coupled massless scalar quantum field. So that is really the simplest that we could consider, and it obeys the Klein-Gordon equation. And this Klein-Gordon equation can be written as the Tucholsky equation or master equation on a Kerr background. And what is remarkable about this equation is that its solution may be decomposed into temporal, radial, and angular parts, which is very useful for computations. So the temporal part, it has this omega over here, it is time translation frequency. That is going to be important. The angular part, because it's not spherical symmetry, it's axial symmetry. So these are the spheroidal harmonics. This is the spheroidal eigenfunction that we are going to see later. And the radial part, thanks to this division by square root of r squared plus a squared, the radial function solves a radial equation, which is a simple equation. It looks like a Schrödinger or scattering equation with this potential over here involving the frequency omega in a non-trivial way. It also includes the spheroidal eigenvalue. So I'm not going to give here the potential, but interestingly, the potential behaves like three different constants at each of the three interesting asymptotic domains. R goes to infinity, it goes like omega squared, which is expected. But at R goes to R plus, which is the event horizon, it goes like omega plus squared. And at R goes to R minus, it goes like omega minus squared, where omega plus and minus are defined in this way. So here I just illustrated the potential outside, looks like a potential barrier, and inside looks like a potential well. And you can see the different asymptotic domains. Okay, so that was just the basic framework. Now let's talk about the Unru quantum state. So we take our field, the massless scalar field, in a state called the Unru state, which corresponds to an evaporating black hole. It is empty at past null infinity, and it involves an outgoing flux of thermal radiation at future null infinity. And the way we define this Unru state is we decompose the field in terms of Unru modes. So this G are the Unru modes. I'm going to show them right now. And the Unru state is a vacuum state with respect to this decomposition. So what are these Unru modes? They are defined in the red frame, and they're defined through boundary conditions. So here is just a reminder on the coordinates. So the in Unru mode, they come from past null infinity as e to the minus I omega v, and v Eddington is linear in t. So this omega here is time translation frequency. That is good because it means that these modes are separable in the Tucholsky way. But the up Unru modes are defined through boundary conditions on the left horizon union with h past, and they come with e to the minus I omega u Kruskal. And the u Kruskal defined in this way, it is not linear in t. So for each Kruskal frequency over here, there are many, many different time translation frequencies. So that means that the Unru modes are non-separable. So in order to compute them, we would need to solve PDEs rather than the ODEs that I showed you before in the Tucholsky decomposition. Okay, so Unru modes are good for describing the physics, but not so good for computations. But there is another set of modes. These are the Eddington modes, which are a mathematical tool, and that's why I introduced them here. So they are separable in the usual Tucholsky sense. They have this e to the minus I omega t and a radial function. And the way they are defined, so they are the exterior Eddington modes defined in the black hole exterior, the up and in coming from h past or past null infinity, and both of them come with respect to the Eddington coordinates u or v. So that means again that we have this factor, this time translation factor here, which means they are decomposable. And similarly for the interior Eddington modes. So for each of these frequencies over here, with which these modes arise, the left and the right modes, there is a single time translation frequency. Okay, so these modes may be easily computed. All we need to do is to find the spheroidal harmonics and solve the radial equation for the radial function. So we are going to use the Eddington modes as a mathematical tool. Okay, good. So now that we know our modes, our two kinds of modes, the Unru and the Eddington, let's talk about the individual mode contribution to the fluxes. So first, what do we want to find? We want to look at the stress energy tensor. So the classical starting point for the stress energy tensor of a scalar field is this expression over here, where phi, of course, is the scalar field. And it's convenient to look at the trace reversed version, which just eliminates this part. So the quantum version, very naively, we can just take expectation value on both sides of this equation. And this is what we call the bare expression for the stress energy tensor. Now, I keep saying that we want to look at the flux components. So what are the flux components? Just a reminder on the coordinates inside the black hole. So the flux components are TUU and TVV, where U and V are Eddington coordinates. And it turns out that these fluxes exist on space-time because of the curvature, and they are crucial for back reaction at the Cauchy horizon vicinity, as we will very shortly see at the end. So that's why we are going to concentrate on these components of the stress energy tensor. Another nice property is that energy momentum conservation yields that this quantity over here, the difference of TUU and TVV times an area, is a conserved quantity independent on R. And when we take this quantity to infinity, it coincides with the Hawking radiation outflux per unit solid angle in the direction of theta. So that is, it gives some physical meaning to what we are doing. Another thing to note is that in Unru state, which is a physical state, it is regular across the event horizon. And that means that TUU is 0 at the event horizon in the Unru state. Because otherwise, when we transform to the regular Kruskal coordinate, we will have a diverging TUU in Kruskal coordinates. So because it is regular, TUU must be 0 here. But the fluxes evolve, and near the Cauchy horizon, we expect both fluxes to be present, both flux quantities. Okay, so as I said, we're interested in the flux components, and especially near the inner horizon. So since GUU and GVV are 0 at the inner horizon, we can take that and we see that the bare inner horizon flux components are going to be just given by that. So minus over here denotes the inner horizon. Y is either U or V Eddington. So we have here just the product of two field derivatives evaluated R at R goes to R minus. So let's focus on TVV just for convenience. So TVV at the inner horizon would look like that in terms of the field derivatives. In terms of the Unru modes, just plugging here the Unru decomposition, we find this very simple sum. But as I said, Unru modes are not very useful for computation. So what we're going to do is take each Unru mode and write it as a superposition of Eddington modes. And when we do that and take the inner horizon limit, we find the following expression. So this we did in this paper over here, if you would like to look at the details. So what we see is that the bare mode contribution for the TVV quantity at the inner horizon is simply composed of S, the spheroidal eigenfunction, A, B, and rho. Rho is the scattering coefficient for the up mode outside the black hole. It's given by this psi up over here. And A and B are the coefficients of the free solution for the internal radial function near the inner horizon. So we can solve for both row A and B. So this expression, it contains all the required information, the individual mode contribution, but when we sum over all modes, it diverges. Okay, so now that we have the bare mode contribution, we need to regularize it. And we're going to do it by state subtraction. So very schematically, the renormalized quantity equals the bare quantity minus some diverging quantity. It needs to be subtracted. And crucially, this diverging quantity is geometric. It is locally constructed, and thus it is shared by all quantum states. And then if we want to compute our quantity in the Unru state, all we have to do is take another reference state, subtract the naive expressions, and add the quantity in the reference state. So that would be useful if this is known. So we now focus on the Unru TVV flux component at the inner horizon. So we have the bare mode contribution for TVV at the inner horizon in Unru, and we would like to find a reference state such that TVV at the inner horizon in this reference state vanishes. So our motivation is going to be based on the Unru behavior at the event horizon. So we know, as I told you before, that TUU at the event horizon, denoted by this plus over here, in the Unru state vanishes, and it has the following bare mode contribution. So we would like to construct a reference state U underbar such that just in an analog to TUU plus in the Unru state vanishing, it will have TVV at the inner horizon vanishing in the U underbar state. So that is our motivation. Okay, so let me illustrate how we are going to construct this reference state. So first, what we want TVV at the Cauchy horizon vicinity. And we denote it by the script C over here. And the Unru state is defined through this red frame. Now we note that the metric extends through a ring singularity to negative R values, reaching R goes to minus infinity, which is an asymptotically flat universe, which we denote by A bar. And now we focus on the blue frame, which corresponds to this A bar asymptotically flat universe. And we would like to treat it like the red frame, which corresponds to the usual R goes to infinity asymptotically flat universe. So the way we do it is we define a new coordinate, R bar, which is minus the original R coordinate. And we define a mass parameter M bar, which is minus the original mass parameter. So we get a repelling rather than an attracting gravitational force over here. So we would call it the negative mass universe. And now, if I replace all the R and M in the form of the metric by R bar and M bar, we see that the form of the metric stays exactly the same. So that allows us to treat this blue frame just like we treat the red frame. And we have horizons. So here all the asymptotic domains of the red frame. We also have a barred analog in the blue frame. So we have EH bar and PNI bar and FNI bar and so on. And there are some more relations relating the blue frame with the red frame. Okay, that is nice. So now that we have established the analogy of the blue frame with the red frame, we can construct a state which we call the U bar state in the blue frame, which is analogous to the U state, the Unru state, in the red frame. So let's continue. Next, we look at the event horizon vicinity. Remember, this was our motivation. So we call this vicinity epsilon. And we know that TUU in the Unru state vanishes at this epsilon over here. And it has the following bare mode contribution. Now we would like to go from the blue, from the red to the blue. So that is from the Unru state to the U bar state, and from epsilon to epsilon bar. So where is epsilon bar? Epsilon bar is just above the EH bar. just like epsilon is just above EH. And then we have that UU in the U bar state is 0 at epsilon bar. And it has the following bare mode contribution, which is just the mapping of this using this dictionary that relates the red and blue frames. But recall what we want is to find TVV over here at the C over here. So how do we relate epsilon bar with the C? So the way we're going to go from epsilon bar to C is do a time reflection through this horizontal dashed line. And that takes the blue frame to the dashed green frame. And we define the U underbar state to be the time reversal of the U bar state that we defined in the blue frame. So going from U bar to U underbar, we go from epsilon bar to epsilon underbar. So yeah, the time reflection of epsilon bar through this line would be over here. And that is exactly the C, the domain that we are interested in the first place. So that is good. And we also note that the U direction in the epsilon bar domain, doing a time reflection, it goes to the -V direction in this epsilon underbar. So that means that just performing this mapping, we have that TVV in U underbar is 0 at epsilon underbar, which is exactly the Cauchy horizon vicinity we were interested in. So that is great. We found a state in which TVV vanishes at the Cauchy horizon. And we have the bare mode contribution that corresponds. So we wanted TVV at the inner horizon in the Unru state. And we found a state U underbar. We constructed it such that TVV at the inner horizon in U underbar state is 0. And we found the bare mode contributions that appear in this difference. So that is great. That is exactly the recipe we were looking for. And this recipe has ingredients which are just the spheroidal eigenfunction, A, B, the internal scattering coefficients, and rho, the external scattering coefficient. And these may be computed numerically, and our colleagues Mark Casals and Adrian Ott can do this very efficiently. So the way we apply this computation is we take the difference in the individual mode level, and then we sum and integrate over the modes. So an important test, of course, is whether this difference indeed regular. Each of these mode sums diverges. And we find, to our great happiness, that yes, we find empirically exponential convergence in both L and omega. So this is good news for the numerical implementation. It means that it is very efficient. Okay, so now we can use this recipe that I showed you to actually compute the Unru inner horizon fluxes for rotating black holes. So now I will show you our numerical results. So first, we look at theta equals 0 at the pole, what we call the pole, because this is easier because only m equals 0 modes enter this computation. So here we see the polar inner horizon fluxes versus the black hole spin. So the black hole spin is the horizontal axis. And here we see a zoom in to this domain over here. So we see that the fluxes, TVV and TUU, both change sign at some value of A over M. And both approach 0 as extremality is approached as A over M goes to 1. So just as a nice remark, it's nice to compare it to what we found in the spherical charged case. So in the spherical charged case, you can only look at the orange and the blue lines. The green is Hartle-Hawking. So you see that in the Reisen-Nordstrom case, we also found that the fluxes change their sign at some Q over M, analogous to A over M value, which is quite close to 1. And both fluxes vanish towards extremality. The difference is that the Q over M corresponding to sign change in the charge case are larger than the analogous spin values of sign change in the rotating case. But that's just a neat comparison. Now, of course, it's interesting to go off the pole and look as a function of theta, the polar angle. So we choose a certain spin, which is 0.8, and we plot both fluxes as a function of theta, the polar angle, here given in degrees. So we see that it starts positive. This point actually existed in the previous graph as well. This is just the pole. And then it decreases. It crosses the horizontal axis. It reaches some minimal value. And then it reaches a maximal value, which is positive at the equatorial plane. So that is something interesting that we didn't know how to expect it. But just note that this is for a fixed A over M value, just one A over M value that we explored. And at other A over M values, it may look different. But again, we see two sign changes over here. And the sign is going to be perhaps important, as I will tell you just now. So our method is new. We use the really non-standard quantum state. So it would be crucial to test our method against our methods to see whether these results that we got actually mean anything. So a standard method for regularization is point splitting, but we don't know how to do point splitting straight at the inner horizon. So we are going to compute with point splitting the fluxes as they approach the inner horizon and then compare. So this is what we do here. The horizontal axis is the log of the distance from the inner horizon. The inner horizon is found infinitely to the left. The points are the values we computed using point splitting. The lines, the colorful lines are extrapolated, and the horizontal dashed lines are the state subtraction results, the values that we got exactly at the inner horizon. And we see that both for TUU and TVV, we find that these point splitting fluxes really approach the state subtraction results at the inner horizon. So we found this agreement to 4 figures. So that is quite good, and it really corroborates our method. Another thing that haven't been published yet is just the point splitting fluxes as computed between the horizons, between the event horizon and the inner horizon. So that might be the topic of a future paper. We also looked at the extremal domain, where I told you where you saw that the fluxes vanish towards extremality, and we looked at it analytically, both analytically and numerically, but I'm not going to go into it because we have no time. It is found in the supplemental of our paper. Okay, good. So now let us finish with a short and really preliminary discussion of back reaction. So first, we found that TVV is generally non-zero at the Cauchy horizon. And that means that if we go to the Kruskal coordinate, which is regular at the Cauchy horizon, we find a curvature singularity, because this factor over here diverges with V going to infinity at the Cauchy horizon. So let's go a little forward into back reaction. So that is going to be very preliminary. But in the spherical charged case, we found that R comma Y, where Y is either U or V, near the inner horizon, it goes like minus the corresponding flux quantity, TYY at the inner horizon. So that means that R comma V in the V direction in purple goes like minus TVV, and R comma U goes like minus TUU. And look at these directions of U and V. So U is the direction of propagation of generators of the Cauchy horizon, and V really goes with our traveler. So that means that the sign of TVV is likely to determine the nature of tidal deformation for our traveler. So if we look at dr to d tau, we see that it goes like minus TVV times this diverging factor. That means that an infalling observer with this dr to d tau undergoes abrupt, because of this factor, abrupt expansion if TVV is negative, or contraction if TVV is positive. So the sinus TVV is crucial for the fate of our traveler. And the sign of TUU might determine the fate of the Cauchy horizon itself. So to summarize, we constructed an unusual quantum state, U underbar. We used state subtraction for flux regularization and computation in the Unru state at the inner horizon. And we found that TVV and TUU at the inner horizon of rotating black holes are well defined, and they have a generically non-vanishing value. In particular, as we saw, that means that TVV in Kruskal coordinates, which are regular, diverges, which means that we have a curvature singularity. And the sign of the fluxes, we found that it depends on both the spin and the polar angle, and the fluxes change sign, and that might have an implication for back reaction. Additionally, we found that both fluxes vanish as extremality is approached, and we compared our point splitting results. We compared our state subtraction results against point splitting results at the inner horizon and got excellent agreement. So in the future, we would like to first extend this current study. So as you saw, we were looking as a function of the spin and of the polar angle. So this is a two-dimensional domain we can explore, and we only looked at two one-dimensional lines in this two-dimensional domain. So we would like to compute the inner horizon fluxes of the pole as a function of theta at other spin values. We would also like to use point splitting to compute the fluxes between the horizons for other spin values and polar angle values. Investigate the near extremal domain, both analytically and numerically, of the pole, because we only did it on the pole. We can perhaps compute other components of the stress energy tensor. And now a more physically realistic thing that we can do is explore the quantum electromagnetic field case rather than the quantum scalar field. And most importantly, for me at least, would be to investigate the back reaction effect, that being the motivation of this whole research. And then we might be able to answer the questions that I raised in the first slide, in the short story. So thank you very much for listening. This talk was really based on this paper. If you would like to read more, if you have any questions, you can write to me or you can ask right now. So thank you very much.
Thank you very much, Noah, for the wonderful talk. So are there any questions? I think there was one question in the chat at some point.
Yes. You were considering minimally coupled, right? Yes, I was considering minimal coupling. So the stress energy does not miss terms. Oh, I probably just misheard. Yes. If it was conformal coupling, the stress energy tensor would look different. But in minimal coupling, it's really just the simple expression I wrote down.
Okay, I see a couple of raised hands. So, John, please mute yourself and ask your question.
Yes, hello, thanks for the nice talk.
Thank you.
Just a basic question. When you had your renormalized stress tensor, you had the difference of the Bayer terms and the renormalized term of a comparison state. I just wondered, so what was the motivation to have it zero? Was it just computational, that it's easier to compute, or what was it? Maybe I missed that.
Yes, yeah, thank you for your question. So indeed, when you want to compute something, for example, in the Unru state, you would take the difference between the Bayer mode sums and add the renormalized quantity in the reference state. So it is very convenient just computationally, like you said, to have it equal zero. So, or equal zero or equal anything else. But it was easy for us to construct the U underbar state, which is our reference state, such that TVV at the point of interest is exactly 0. So all we need to do is just subtract the bare mode sums. So yes, it's for computational. Yeah.
Okay, thank you very much.
Thank you.
Next, we have a question by Johan. Please unmute yourself.
Okay, hello. Thanks a lot for your very nice talk. I have a short, probably I just missed the point, but so you showed how to compute this TVV component of the stress tensor, but you also showed results for the TUU component. So at some point, I think you mentioned that it's related to a conserved, these are related by conserved quantity. I guess this is how you compute it, but perhaps you can elaborate.
Yes, yeah, it's a good question. Thank you. So yes, indeed, the TUU and TVV are related by a conserved quantity. I can also write down TUU minus TVV, the mode contribution. But the fact is that TUU minus TVV is regular. So if I regularize TVV, I can find TUU easily. So what we did was indeed just compute TVV and add this regular piece, which gives us TUU.
Okay. Mm-hmm. Good. Thanks a lot.
Thank you.
Okay, next we have a question by Julio. Please go ahead.
Thank you, Noah, for the talk. I have a very simple question concerning the back reaction implications. The fact that the sign of the components of the stress energy tensor depends on the angle. Do you expect that the back reaction deforms the horizon away from sphericity because of that? Or?
Away from what? I'm sorry, didn't hear.
I mean, having different signs depending on the angle, do you expect like local contractions and expansions of the horizon depending on the angle?
Oh, yes. Yeah. So that is something that, again, the entire back reaction was just very preliminary. We still would like to investigate it. But indeed, the different signs that we see as a function of theta means that we will have, perhaps for an infalling observer, expansion, like local expansion and contraction as a function of theta. Yeah. But again, this needs further investigation to really give a full picture.
Okay, thank you.
Okay, we have one final question in the chat. It says, thanks for the nice talk. Do you think these analyses on the Unru state for the maximally extended Kerr solution will be representative of what happens in a black hole formed by a collapse?
Yeah, that's a good question, because so indeed, that is why we only considered the ingoing section of the inner horizon as the Cauchy horizon that is motivated by collapse, but scenario of collapse, and also the Unru state at long times should be a very good approximation to what happens in collapse. So indeed, our motivation is collapse, and although I showed you throughout the talk just the Kerr metric, we do expect that our results will carry on to collapse. Yes.